Yeah, welcome everybody. I'm going to talk about FUDGE, which is a library we wrote, which can be used for integration testing. And yeah, my name is Centrifuge. I work at Centrifuge. I'm a Rust dev there, and also worked quite a lot on the FUDGE library. And I'm going to start to talk a little bit about the current testing that we have in Substrate right now, and from there on going to show some of the issues that I think that they have because of the scope of the testing, and from these issues maybe derive some of the requirements that a possible solution should provide in order to actually enhance the testing possibilities that we currently have. And then I'm going to talk about the library that we wrote, the main structure of it, and show you a little bit how the internals work. And this should take roughly 20 minutes, I guess. And then we will have a hands-on section where I'm actually going to use the library just to show you that it's not just things that I thought about, but things that actually work right now. And in the end, we will have hopefully a little bit of time for questions if there are any. So the current testing that Substrate currently provides is basically unit tests and system testing. And the unit tests are, from a runtime perspective at least, the unit tests are the Pallet Tests that we currently have. And I guess we have a lot of Substrate devs here, so all of you probably already set up one of those Pallet Tests. And in the beginning, you usually set up some artificial state that you need, maybe pallet balances, I don't know, anything that the traits that you use depend upon. And then you have the state where that is actually used when you run your test cases in this externalities provided environment. And this state is quite static because there's not a notion of let's move to the next block. It's just the state at a specific point in time, let's say so. And then usually you would have some maybe mock traits depending on what kind of functionality your palette depends on, and you might also have some mocked types, depending on what you actually need. And then test networks are basically the other extreme, the system testing. Those are the system testing things that we have in Substrate, and this can be like a local network. But this also can be like a virtual private network or a public test network, like Rococo, for example, would be one of those. And those are basically, this is the complete consensus system that you actually have started. So you have signatures, you have authorities, you can connect your front end, maybe a block indexer, like anything that your real system also can use, you can also use there. And why do I think there are some issues with it? Well, for the unit testing, this is basically, the unit testing tests your palette isolated from how it's going to be used in the actual runtime. So you will probably have different types. At least we at Centrifuge always have the unsigned 64 as the account ID, while in the actual runtime we use the public key of a public-private key encryption scheme. But for me at least, the most important thing is that you're probably going to have different code paths depending on what you do, because once you mock a trait, you definitely will have different code path execution in your actual runtime when you use the trait that you're actually going to use in your runtime compared to what you tested in your unit tests. And incomplete state is a little bit hard to actually simulate the progression of blocks. For example, it's really hard in a unit test to actually, for example, generate persisted validation data, which is the data that you get from the relay chain. And for the test networks there, this is actually testing, test networks are definitely testing what you're actually going to use in production. But at least from a development perspective, it's there's quite some overhead to actually, for a parachain, for example, start your network, onboard your parachain, let it produce some blocks. Well, I probably should stop notifications. So, yeah. So, yeah, this is easier. All right. So you have the time overhead, but you also have like no debugging. Like it's a running machine. You cannot simply just start a collator and debug through it. So this is not possible. And it's also sometimes quite hard to get the right locks. For example, you have access to the locks of the relay chain. You have access to the locks of your parent chain. But so, for example, if you have a connection with another parent chain and you're maybe in a public test network, it's not super straightforward to actually see what's going wrong or what's actually wrong on their side at the end. So, all right. A possible solution for this, like the integration tests is basically a perfect solution for this one, because the runtime is basically a composition of independent or mostly independently developed modules who are like wired together into like one complex structure, and you want to see if all of the units that you actually generated there, that they actually work correctly when working together, And of course, it's important that you also have tests for, well, is my consensus system working correctly, and can I connect my front end? But integration tests are basically this middle thing between unit tests and system testing, which is like faster to develop upon, but has like more security guarantees than the unit tests. And what do you actually need? So what are the requirements if you actually wanna do integration tests in Substrate? Well, you definitely need real block building, and mostly this means that you need to generate correct inherents, you need to generate correct digest information, you need to include extrinsics correctly so that you can actually progress your chain locally, like without a network. You would need to have access to the state of the chain, so that you can check, like, against some invariants that you maybe defined. Just execute your test cases, basically, given on some state. The manipulation of state is probably just interesting if you want to have like a given database, and what you want to do is manipulate it so that you can use it for different circumstances. You might want to like simulate a bug or something like this. And warping time is like the control over the timestamp, because like your blockchain doesn't have a notion of time. It just like has your timestamp that you give it to it. And this is especially important for us. This was always important because we basically want to know how a chain, or how a chain looks like a year from now, if you have like a timestamp in a year from now. So yeah, it would be nice if you could like warp time with your timestamp like this, because you don't want to have a test network running for a year to actually check what's there. So yeah, all of this has basically been my argumentation for why FUDGE is a useful library, and why it can be used. And what FUDGE does is actually it's just something that gives you access to the core traits that's like any substrate-based chain currently is based on or built upon. And we at Centrifuge hope that by giving you like a simple way to actually access and use those functionalities, that you will be able to like build tools on top of that can be used for analyzing your state, or maybe just easing the development experience that we have in general with Substrate. And let's see if this is actually possible, but this would be the ultimate goal. And I'm going to talk a little bit like how FUDGE is actually structured, and what are like the core components and how they work. So like there's everything that you do with the library is basically built upon builders, like on this notion of builders. And we currently have like the parent chain builder, a relay chain, and a standalone builder. And why we have different ones, I will explain later on. But all of those at its core just wrap the core builder that we have. And the core builder then is actually the one that handles all the hard lifting of stuff. So it gives you access to the traits of a client, like client-related traits, pool-related traits, and backend-related traits. And, well, I'm on time. And so why do we have different builders? Well, the main reason why it makes sense to have on top of the core builder, to have like different builders on top of that, is that the runtime or the expectations that you have on the runtime API of a paired chain are completely different compared to the relay chain runtime API. And the standalone builder basically is just a shim layer, which has like a user-friendly API. It's just a little bit nicer to use than the core one. But for example, the relay chain builder actually expects the runtime to implement a runtime API that can generate persistent validation data. There's a method to actually onboard a paired chain builder. And it actually needs also the runtime, you know, the runtime, this is totally wrong, but it actually needs like the real runtime to be provided, because we need to manipulate the storage of the database currently to onboard the paired chain, because we don't have signatures, but this is like too much detail. And the paired chain builder on the other side can provide a FUDGE specific collator that the relay chain takes, currently the relay chain builder. And this will provide the relay chain builder with some information about which blocks should be imported and stuff like that. And the core builder, like this is like those are basically all the trade bounds that you have on the core builder. And as you can see, it's generic over six data types basically. So it's generic over the block, it's generic over the runtime API, over the executor, over the backend, over the client, and over the transaction pool, you know? And as long as, you know, the data structures that you provide satisfy actually what the generics expect, you can just wire in whatever you want to. But yeah, there are some helper methods that will just instantiate the standard types that we currently, like, at least to the best of my knowledge, that I have not seen a client or a custom client implementation by another team so far. But what the helper methods basically do is they just instantiate the normal client, the full backend, and the full pool, and then will help you like starting the builder. And the builder is then, you know, this core builder is then basically taking care of, opening up the database, you know, at any point in time that we currently have in the database, like any state that you have, and then you can like execute any code that you want in this externalities provided environment. It takes care of mutating the latest state that is in the database, and it also takes care of building and importing blocks. And how does FUDGE build and import blocks? Well, like in this flow chart, what you should see, this is like a really simplistic flow chart for how we import blocks. And usually, what you get a notification from the network that you have received a block, and the consensus input queue then takes care of actually checking if this block is valid from a consensus perspective. So if the signature is the right one, if it's an offer that should be submitting or should be building the block at this specific height and something like this. And afterwards, the block is basically funneled down to the lower level importing logic of the client. And what FUDGE does, it simply skips the whole consensus part, and we just import it directly because it's all local. And then there are like no consensus checks. You don't need to worry about signatures and stuff like that. And this is basically the thing how we import things. And for the block building, FUDGE tries to mimic the node logic as close as possible. So this is like the code snippet from, and yeah, there are a lot of unwraps. It's like we're past proof of concept, but we're like cleaning up error handling and everything. But what you see here is like we're using the normal proposer factory that basic authorship of Substrate uses, and as long as your pool, for example, will provide extrinsics correctly, they will be included just like on your node, for example. But as you can see, you know, the function actually expects you to provide correct inherent, correct digest information, a time, how long it should take, and a limit. And then, yeah, then we simply import it. And then we simply build it, propose it. The importing differs quite significantly because we always import a block as finalized, and the reason for that is that if you manipulate a database or if you just build a block, if you build a block, we want it to be finalized so that you can actually start your client or your node on top of this thing, and your node is thinking, well, this is the last finalized block. Yeah, should be on time. And yeah, this is the feature that probably gave me most headaches, but it's also the one that I personally find the most interesting one. This is FUDGE allows you to you can open up the database at the last state basically that you have, and then run any logic that you want to run in this externalities provided environment. Like, for example, think about like externalities from the test cases, and then you have like some arbitrary mutation. And what FUDGE is doing, it's then finalizing, persisting this state to the database below, actually. And how this works is, the database, of course, always expects a block in order, you have state A, then you have a block, and the block brings you to state B. So a block is the only thing that can actually mutate your state to a new state. So we're telling the database, hey, we're going to start an operation, and then, as you can see, the externalities provider there will actually generate externalities, and then we execute the closure that you provide as a dev, we execute it. And the externalities basically catch all changes in the overlay, and what we're doing then here at FUDGE is that we are draining this overlay, and what this does is basically say, given the state and given this overlay changes, what is my new root? And what are my storage changes that brought me to this root? And nothing is in the database yet. And what FUDGE is doing then is basically retrieving the latest header. We just artificially set for this header, set the new root, set the storage changes, and then we commit everything to the database. And this works, but you really must be sure that at this point in time, you have like this artificially changed block here, and if every node in your network starts from this block, it's fine because this is like the last finalized one. But every node that syncs from 0 against this node will basically import node X, and the root from the syncing node, the root that is coming out of block X is totally different for the one that's synced from 0 because the storage changes FUDGE introduce are not coming from a block at all. So you're basically breaking your chain. So yeah, this is why it's for tooling. And I think, yeah, I can go through some examples. Well, I just show you one. So this is like the bare minimum example. Like state provider is just a helper that actually can provide genesis. The initiator is also a helping struct that will help you instantiate client, backend, and pool. And CIDP-DP is basically a closure or just anything that provides something that can generate inherent data and something that can generate a digest. And this one is empty right here. So if you, for example, would have timestamp in your runtime, this would basically error out when you try to build a block because timestamp wants to have like an inherent that actually sets the timestamp. And then I can show you, yeah, this is also one interesting thing is we also build a macro, which is the companion macro, which will take multiple pair chain builders and one relay chain builder, and basically just wraps them together and builds like easier to use methods so you can like basically evolve a whole network without taking care of calling building block explicitly for every pair chain. Yeah, and I would say time-wise. So yeah, I coded everything up front because otherwise, yeah, I would be like not getting anywhere soon. What this is doing here is we have like this helper method that I wrote here basically is a standalone builder, and you can see, here's the standalone builder. We're dependent on the Polkadot block. We are dependent on the Polkadot runtime API. We are also using the inherent data provider that Polkadot actually expects. But we have like a FUDGE specific timestamp, but we have like correct BAPE. We have like inherent data provider is correct, but we don't have the correct inherents that you actually would expect on the relay chain side when you have like backing of pair chain blocks, for example. So this is dummy just, and this is one of the helper methods or functions. Actually, it's a function that I talked about, and what this is expecting is like a handle because it's async, and we need it in order to spawn tasks, and something that can provide you with a backend, but it's like not the real backend, but rather the backend provider. So think about disk-based or in-memory based. And then here you see like we have the default client, which will be the T full client, and we're using a WASM executor. But you could also use a native else WASM one. And then we set the Genesis one, that we're getting here. Like this is Genesis, and it builds storage, and then we just instantiate a standalone builder, and get everything we need. But the in-memory one is basically blank. So if we provide nothing here, this will be storage default. And if I run it, you will get a panic because the first time you instantiate a client, it basically expects code like your WASM blob to be available, because you need to retrieve the current state version from your WASM blob, and this is not available. And so this will basically only upon the generation of T full client, you basically get an error here. But if we use Polkadot runtime, wasn't binary. Yeah, this should work. Yeah. I need this one. Yeah. If we like the state provider is just a convenience struct for you to actually, you can provide multiple Genesis storages, like from your pallets or something like this. Yeah, this error is a resource thing that I'm not sure why it's currently happening, but you see like the client here actually generates a Genesis block, and then it's like in memory. So yeah, the error on the essential transaction pool task happens sometimes. So just here. Yeah, and this is one example where which shows a little bit more of what you can do. We have our Polkadot runtime. We again have in-memory in-memory database. So we're using in-memory database. Then we build a block, we import a block, and do this twice. And this method here, the with state add, basically is the method that opens up the database at a given block ID, and we want it to be opened up at state 1, and then you can execute code like at block 1, And imagine if you have like a real database, then you can like have like analysis over multiple blocks, and you can just have like any code running on the state that we have. And I am actually going to, remove the mutation that you see that it's actually working. So like the first thing I'm doing here is like I'm opening up the database at block 1. With state basically opens up the database at the latest available point. So this should lock just 2, we are getting block number 2. And then at the latest block, I'm basically getting the account ID information for my account and lock it again. And then, I changed this from mutable to just with state. And, I can do mutations here, but if I don't use the mutable method, then it will just not be persisted to the database. So you will see, if I log it again afterwards, it should just be the same than it was before, before I executed this closure. Yeah, I don't have an M1, it's pretty slow. Yeah, you get all the logs that you usually get when you build a block. We have no migration. Of course, the randomness is not right because we don't have any signatures, so there's no entropy available. But you can see my account info basically is the same, so I have no free balances, although we executed this one here. But if I actually start it like this, yeah, then you can see, now the database basically contains my mutated state, although, it came just from the closure. So you can basically do anything you want with the database at this point in time. So let me comment that out quickly. All right. And the next example I'm going to show you is where I'm going to use the companion macro that I showed you earlier on. So this test env is basically a structure that is defined like this. We have like a dummy parachain that just has like a minimal runtime specification, but has of course its own block, has of course its own runtime API. You can provide like any parachain ID that you want to provide. Then we have like Centrifuge, which is our actual runtime, from our repository. And then we have like Polkadot here. And setting this up is a little bit more tedious because you start your relay chain first. We have our blob here. We insert it, and then we get a builder. And the parachain, what the parachain expects is, as you can see here, the relay chain structure that the builder that we provided has like this thing which I call inherent builder, and this is basically the inherent builder is basically creating the parachain inherent data by actually accessing the current state of the relay chain. And then it generates like it grabs the persisted validation data and generates everything that the relay chain would actually get from the relay chain. So it's just needed in order to generate the correct inherence for a parachain. So we need to do this here. One inherent builder for the dummy chain and one inherent builder for the centrifuge chain. And because, for example, we are using Aura here, we need to, like, those are dummy authorities because we started cleanly at the beginning. Usually when you have like an already existing database, this should already be in storage. And then, we just generate the test environment here. And and what I'm doing here is I'm basically evolving it, which means I build 2 relay chain blocks and then I build one parachain block, well, one relay chain block, one parachain block, one relay chain block, and go on and go on. And what I do here in this method is, I'm opening up so this is the test environment, and the with state method is a little bit different. It takes an enum, which is chain, which is either one variant is relay and one variant is here para, where you provide the para ID so that the builder actually, that this macro generated structure actually knows which database to open. So we are opening the relay chain, and then we are actually fetching the current para head, that is the view of the relay chain, or the view of from the relay chain of each parachain currently. And then afterwards we are here in this one, I'm actually using the centrifuge specific builder directly, and this head method basically retrieves the latest header here from the blockchain database of the parent chain. So what we want to do is we actually want to check if the view of the relay chain is the same than what the parent chain actually thinks of itself. All right, this will take I noticed that I forgot something. While this compiles. So yeah, like 3 Genesis blocks, and then we have like Polkadot block building, we have like dummy block building, and then we have Centrifuge block building. And then you see, Polkadot latest block is 2, we build 2, and because for here in the helper method, I used basically I used a disk DB. This is like we're actually creating a disk database, and what you can see here is just like we have like a normal database that you have like on every node. This is like Centrifuge, Polkadot, and they're like actually disk DBs right now, and the dummy one is actually running on an in-memory one. And if you run it again, you will see that we're using the existing database. So you will see 1 Genesis block, and Polkadot will be on 4, and Centrifuge will be on 2, while dummy is always still on 1. Let's wait for the logs. Yeah, so it's 4.2, and this will like go on and on and on because yeah, there's like nothing changing. And yeah, I'm a little bit faster than I thought. So let me comment that out. And I also, thanks to Miguel, I also actually got a copy of our current collator database. This is like the actual Polkadot database, which I didn't know that, but we only store like 256 blocks, so we cannot query the first one because it's not available. But what you can do is like we can get the latest council information. Let me compile this quickly. So we are getting the latest council information here. This is just I hope it's always at the right path. Should be. Taking quite some time. Yeah, and this is like the latest council that at the point in time where I got the database. So like Gavin is prime currently. You have Raul, you have Akala here, Sean. This is like everything that you have in the council currently. And yeah, I'm going to show this one later. And what you can do is we can, of course, also make me prime. So what this is doing here is, we have a disk builder again, and then I'm logging the council before the mutation. And what I'm doing then is basically I'm filtering out the current prime member, who is Gavin. And then, I push myself, and then afterwards here, we see if it was actually persisted to database. I never checked it with this database, so let's hope it doesn't break my neck here. And the interesting thing about this is, well, okay, nice. Yeah, okay, well, this doesn't work. All right, yeah, this is a perfect example of live showing something. Yeah, so if this would have worked, the nice thing about this is that you can actually have a database where the reason why we developed FUDGE at the beginning was we had a problem where we ran into some issues where we had a migration that was totally fine in the test networks. Like there was nothing actually troublesome for us, but when we ran it in our live network, the database depth was so huge that the migration in the real network, although it had we were migrating vestings, and although the vestings were equally sized in a test network and the real network, because the the database was actually so differently in depth that it took I don't know, in the test network it worked, and in the real network it took 14 or 20 or 30 seconds. It was really huge. So all the time we wanted to do this in the real network, basically we were over the boundary for the block production from the relay chain. And what we did was using an in-memory database at the end, which worked because in-memory was just 100 times faster. But we just had the idea that it would be really nice if you could get a real copy of your database and just switch out all the authorities, change it to def accounts, for example, and then start it again. And then you have all the history. You have, I think we had this in a previous talk, you have the database is still the same, and then you can run a migration, and you can be sure that it will, or you can be sure that it will actually work in your real network, because the database depth, and this is the time it takes to iterate through the try upon translating values, for example, will basically be the same in your test network than in your real network. Yeah. All right. I actually am through right now. So yeah, thanks for listening. And if you have any questions, feel free to ask them.
Questions?
Hello. Thank you for that. So given that you can do a fork test with a real node, you can you can do fork testing using a real node by downloading the current state and importing that as your genesis block for a new chain. What advantages do you see FUDGE giving over just testing against the a real node and doing some TypeScript tests with instant sealing?
What do you mean advantages over the last example that I talked about?
As in, what does FUDGE give you over just doing normal TypeScript tests?
Well,
with instant sealing turned on.
For example, we have this problem. I'm not sure if I have our database open. I'm working on something here. So, we already have some integration tests in place. For example, here. And what we're doing is, you can always start a network, of course. You can always start a network and maybe have some JavaScript code and throw some stuff in there. So I would say if you want to have final tests, or that you run once a month, for example, or once a week or something like that, actually give you, after some big release, you actually check if your chain is still doing what you expect it to do. But the reason for integration tests is currently, the iteration speed that you have is much faster if you can do everything, if you can have a local Rust-based, you can have a Rust code test, and you can run it directly. If there's an error, you can debug through your code. You will have instead of always spinning up everything, running it, noticing maybe through a log that there is an error, looking at your code, maybe have another log then, you could just, slowly debug through what's actually happening. And then, of course, you cannot debug through the WASM one, but you should be able to debug through the native, if you started with a native one. So I would say, depending on what you want, there's no advantage, if you just don't care. But we noticed that the more integrations we actually have right now, for example, the development speed when you have like an XCM integration is insanely slow, because for example, we need to deploy something on Moon Alpha, so it takes like roughly a day if you have it updated. We run our test case and then we notice, well, it doesn't work again. So, and the main reason is there might be no advantage for some teams, but currently it's really hard to actually use the database that Substrate has without calling, for example, an RPC to actually give you all the state. And you only get storage keys in the end. It's just like you need to basically rebuild. For example, here I didn't show you this example, but you would need to rebuild all of this basically. You need to have because vesting changed, and I wanted to show you some vesting. So at an older state, the vesting that you get is basically a different type, but you need all these scale encoded information is basically lost. And if you want to have everything in Rust where you have all the types, it's just much simpler to actually work on it directly rather than having this layer of JavaScript in between. Yeah.
And sorry, bonus question. Have you got this working with parallel execution? So running multiple...
No, it's not optimized. It's like we had this POC to actually see it, so it's all... I'm not sure if we're... Well, the transaction pool works in parallel, but then there's always an await. So I'm totally not sure what the performance is. So, yeah.
Thank you.
You're welcome.
Is there documentation?
No. But we got we got a grant. We got a grant from the Treasury, so there will be documentation. But it's been I've been cleaning up quite a lot. But it's been in the last one was like me hacking around, and then it was then I cleaned it up, and now there will be error handling and there will be documentation, everything. But currently it's just code is docs. Just like everywhere currently in Substrate, I would say slightly, but yeah.